Two civilizations have never met. Not in the sense that we know of two civilizations and confirm they have not encountered each other. In the deeper sense, the one that follows from the physics of the universe, we have reason to believe that no two technologically capable civilizations have ever been in physical contact anywhere in the observable universe. This is a strong claim. It deserves justification, and the justification runs through physics, not pessimism. The universe has built into its structure, into the geometry of space, the speed of light, the rocket equation, the biological constraints of organisms that evolved on planetary surfaces, the specific distances between stars, and the thermodynamic arrow of time. A set of barriers so comprehensive and so deeply woven into the fabric of reality that the meeting of two civilizations from different stellar systems approaches impossibility as a physical limit rather than merely a practical difficulty. Not impossible in the colloquial sense of very hard, impossible in the technical sense of approaching zero probability, given the constraints that physics actually imposes on any physical system, anywhere in the universe, at any level of technological development. Tonight, we are going to follow the argument carefully, layer by layer, barrier by barrier, without shortcuts and without the convenient narrative that civilizations in science fiction use to paper over the physics. By the end, you will not merely understand why civilizations cannot meet. You will feel the weight of each barrier individually, and you will understand how they compound, how each layer of impossibility is not added to the others, but multiplied, producing a total barrier that is not the sum of its parts, but something categorically more severe. The universe is not indifferent to whether civilizations meet. It has structured itself through the laws of physics to make it essentially impossible. Let us find out exactly how. If the night is long, stay. Start with the most basic fact, the one that makes everything else worse. The universe is old, approximately 13.8 billion years old. This number is well established, derived from multiple independent lines of evidence, from the temperature of the cosmic microwave background, from the ages of the oldest stars, from the expansion history of the universe measured through Type 1a supernovae. 13.8 billion years is a long time. Long enough, in principle, for a civilization that developed early to have had enormous amounts of time to spread, to build, to signal, to do anything that any intelligence might conceivably want to do. The Milky Way has been producing stars for approximately 13 billion years. Many of those stars are significantly older than our Sun, by 1 billion, 2 billion, 3 billion years. If Earth-like planets form around Sun-like stars, and we know from the Kepler and TESS surveys that planetary formation is common, then some of those older stars may have had planets capable of supporting life for billions of years before Earth existed. If life emerged on such a planet, if the chemistry and the conditions were right, that life has had billions of years of additional time to develop, to evolve, to produce intelligence, to develop technology. Billions of years more than us. A civilization that has been technologically capable for 1 billion years has had 1 billion years of additional development beyond our current state. The gap between what we can do now and what such a civilization could do is not merely one of degree, it is one of kind. We cannot even meaningfully describe what technology looks like after 1 billion years of development, because every projection fails to account for discoveries and capabilities we cannot yet conceive. This should produce observable consequences. A civilization with 1 billion years of development should have left marks on the universe that we could detect. Megastructures, engineered stellar systems, directed signals, galaxy-scale modifications. The universe is old enough that such marks, if they exist, should be visible. We see nothing. Not a single confirmed artifact of any extraterrestrial civilization. Not one megastructure. Not one clearly artificial signal. Not one modification of any stellar system that cannot be explained by natural processes. The sky is electromagnetically quiet in the ways that would matter. No structured radio signals from beyond our solar system have been confirmed in 6 decades of systematic searching. This is the Fermi paradox. And it is not a paradox in the sense of a logical contradiction. It is a paradox in the sense of an unexpected result, a result that contradicts the naive expectation from the apparent conditions. The naive expectation, a large, old universe with common planetary formation and a long time for life to develop, should produce detectable civilizations in abundance. The observation, nothing. The resolution of this paradox matters enormously because different resolutions have radically different implications for whether civilizations can ever meet. Some resolutions, the Great Filter, the rare Earth hypothesis, the hypothesis that intelligence is vastly more improbable than we assume, suggest that civilizations are extremely rare, perhaps unique, and the question of meeting is moot because there is no one to meet. But tonight we are not taking the easy resolution. We are taking the harder one, the one that requires engagement with physics rather than demographics. We are going to assume that civilizations exist, that the universe contains intelligent life in multiple locations, and ask what the physics of the universe does to any attempt by those civilizations to make contact. Because even granting the existence of multiple civilizations, the physics imposes barriers that are deeply underappreciated. Begin with the simplest barrier, distance. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. In kilometers, approximately 40 trillion. At the fastest speed we have achieved for any spacecraft, Voyager 1's 61,000 kilometers per hour, the journey takes approximately 73,000 years. 73,000 years to the nearest star, which may or may not have a habitable planet, which may or may not have developed life, which may or may not have produced intelligence, which, if it has produced intelligence, may or may not have produced technology at a time that overlaps with our own. The last condition, temporal overlap, is the one that receives the least attention and deserves the most. Consider the specific situation. Our civilization has been technologically capable of interstellar communication, capable of broadcasting radio signals that propagate at the speed of light for approximately 120 years. The first radio signals we broadcast have now reached approximately 120 light-years from Earth. Within this sphere of 120 light-years, there are roughly 14,000 stellar systems. But the sphere of our electromagnetic visibility is tiny compared to the galaxy. The Milky Way is 100,000 light-years across. Our electromagnetic footprint, the region of the galaxy that could have detected any signal indicating our presence as a technological civilization, is a sphere 120 light-years in radius, embedded in a disk 100,000 light-years across. The fraction of the galaxy's volume within our electromagnetic footprint is approximately 0.0000017%. We have announced our presence to a nearly negligible fraction of the galaxy. But this cuts both ways. A civilization on the other side of the galaxy, 100,000 light-years away, has had no access to any information that we are here. The light from our first radio transmissions will not reach them for another 99,880 years. The electromagnetic information that we exist has not crossed most of the galaxy. Now consider the temporal dimension more carefully. Technology is fragile. Civilizations rise and fall. The ancient Romans had concrete, underfloor heating, and a postal system spanning a continent. Then Rome fell, and in the following centuries, the specific knowledge of how to make hydraulic concrete was lost in Europe. Knowledge that took generations to develop was erased in historical eye blinks. The average duration of a technological civilization, the period during which it broadcasts electromagnetic signals detectable from neighboring stars, is completely unknown. It might be tens of years. It might be thousands. It might be millions.
We have exactly one data point, us, currently in our first 120 years. But the range of plausible values is enormous, and the implications are severe. If the average technological civilization broadcasts for 1,000 years before some catastrophe or transition ends its electromagnetic period, and 1,000 years is optimistic given human history, then at any given moment, the number of simultaneously broadcasting civilizations in the galaxy is small. The galaxy has been producing stars for 13 billion years. If the average gap between the emergence of successive technological civilizations in the galaxy is even a few thousand years, then civilizations are broadcasting at different times. They are not simultaneous. They are separated not just in space, but in time.
A civilization that broadcast 10 million years ago and then went silent for whatever reason has left no detectable trace by now, except the fading electromagnetic shell of its transmissions, propagating outward at the speed of light, weakening with the inverse square of distance, already below any detection threshold we could conceivably deploy. The temporal dimension of the meeting problem is as severe as the spatial dimension. Two civilizations must not only be close enough to communicate, they must exist at the same time, broadcasting during the same cosmic moment for any exchange to be possible. Now let us think about what the speed of light specifically does to any attempt at communication across these distances. Light takes 4.24 years to cross from Earth to Proxima Centauri. A message sent tonight to any civilization there would arrive in 4.24 years. Their response, if any, would arrive here in another 4.24 years. Total round-trip time for one exchange, 8.48 years.
8.48 years per exchange to the nearest star. At the scale of the galaxy, to a civilization 50,000 light years away, the average distance to a random point in the Milky Way, the round-trip time for a single exchange is 100,000 years. Consider what a conversation means at this time scale. You transmit a greeting. 50,000 years pass. A civilization receives it. If they are still there, if their technology can still detect it, if their civilization still exists. They respond. 50,000 years pass. The response arrives at Earth. If we are still here, if our technology can still detect it, if our civilization still exists. 100,000 years for a single exchange. The entirety of modern human history, from the first cave paintings to the present, spans approximately 40,000 years. A single conversational exchange with a civilization on the far side of the galaxy spans more than twice the entire history of human art and culture. The light speed limit does not merely slow communication. It makes the concept of a conversation, of an interactive exchange of information between two parties who are both present, essentially meaningless at interstellar distances. What is possible instead is broadcasting and archiving, sending a message into the void and accepting that you will not survive to receive any response. This is not a technological limitation. It is a structural feature of the universe, built into the relationship between space and time that Einstein's special relativity describes. Nothing in physics, no discovered principle, no theoretical framework, no engineering achievement, allows information to propagate faster than light. The constraint is absolute. Now let us think about what the speed of light means, not for communication, but for physical travel,
and why physical travel between stars is in a different and worse category than electromagnetic communication. Electromagnetic signals travel at light speed. Physical objects cannot. Not because we lack the engineering, because the physics of special relativity makes it impossible for any object with mass to reach light speed, and increasingly expensive to approach it. At 10% of light speed, 30,000 kilometers per second, the journey to Proxima Centauri takes 42 years. At 1%, 3,000 kilometers per second, it takes 424 years. At the speed of Voyager 1, 0.006% of light speed, it takes 73,000 years. These numbers are the travel times in the reference frame of the source and destination. Special relativity provides time dilation. Moving clocks run slow, which reduces the subjective travel time for the crew of a relativistic spacecraft. At 99% of the speed of light, the journey to Proxima Centauri takes approximately 4.28 years as measured from Earth, but approximately 7 months as experienced by the crew. At higher fractions of light speed, the crew's subjective time compresses further. But the energy required to reach these velocities compounds catastrophically with increasing speed. For a spacecraft of modest mass, 1,000 kilograms, about the mass of a small car, reaching 10% of the speed of light requires approximately 4.5 times 10 to the 21st power joules of kinetic energy. This is approximately 75% of the entire annual energy consumption of human civilization. For one 1,000 kilogram spacecraft, one way. At 99% of the speed of light, the energy required for the same 1,000 kilogram spacecraft reaches approximately 5.4 times 10 to the 22nd power joules, roughly 90 times global annual energy consumption, one way. And the rocket equation compounds the problem further. A rocket that carries its own fuel must also accelerate the fuel. The fuel required to accelerate the fuel requires more fuel. The total launch mass for a round-trip mission grows exponentially with the target velocity, faster than any energy production system could plausibly supply. For a crewed mission, carrying the life support, food, water, radiation shielding, and all other systems required to keep biological organisms alive for decades or centuries, the mass is far larger than 1,000 kilograms. The energy requirements scale accordingly. These energy requirements are not merely beyond current technology. They are beyond the plausible energy budget of any civilization confined to a single planetary system. To send a crewed starship to even the nearest star at any meaningfully fast velocity requires harnessing energy resources comparable to the total output of the Sun, and sustaining that energy commitment for the duration of the mission. This is the second barrier, energy. Not a barrier of will or investment, but of physical scale. The energy required for interstellar travel at any biologically relevant speed exceeds what any planetary civilization can plausibly access. Now let us think about the biological barrier, because even if the energy problem were solved, the biology of interstellar travel imposes its own fundamental constraints. Human beings, and by extension any organism that evolved on a planetary surface, were designed by evolution for a specific environment. Earth's gravity, Earth's atmospheric pressure, Earth's radiation environment, Earth's day-night cycle, Earth's temperature range, Earth's food supply. Remove any one of these and the organism is in serious difficulty. Remove all of them simultaneously for extended periods and the difficulty becomes existential. In microgravity, the condition of free fall during a spaceflight trajectory, the human body undergoes a cascade of physiological changes. Bone density decreases at approximately 1 to 2% per month without countermeasures. Muscle mass decreases. The
The cardiovascular system reorganizes around a condition where it does not need to pump blood upward against gravity. Fluid shifts toward the head, elevating intracranial pressure and causing changes in vision. The immune system function alters in ways that are still incompletely understood. 6 months on the International Space Station, a short mission by the standards of interstellar travel, produces measurable degradation in multiple physiological systems that requires months of rehabilitation on return. Some changes appear to be long-lasting. For a 40-year journey to Proxima Centauri at 10% of light speed, the optimistic scenario, the crew would spend 40 years in some combination of microgravity and whatever artificial gravity rotating sections of the spacecraft could provide. The cumulative physiological toll of 40 years of even partial gravity deficit, sustained radiation exposure, and enclosed environment is not established by any human experiment because no human being has attempted anything approaching this duration. Radiation is the specific threat that most constrains the duration of any interstellar mission. In deep space, beyond Earth's protective magnetic field and atmospheric shielding, the radiation environment consists of 2 components. The first is solar energetic particles, high-energy particles ejected by the Sun during flares and coronal mass ejections. Within the solar system, these can be significant, but are manageable with appropriate shielding during transit periods near the Sun. The second, and for interstellar missions the dominant hazard, is galactic cosmic rays. These are high-energy particles, primarily protons, but also heavier nuclei, that originate outside the solar system, accelerated by supernova remnants and other energetic astrophysical events. They arrive from all directions, with energies ranging from millions to billions of electron volts. They cannot be fully shielded against by any practical amount of material. The most energetic cosmic rays punch through meters of lead. On the International Space Station, which is still partly shielded by Earth's magnetic field, astronauts receive a radiation dose of approximately 50 to 150 millisieverts per year, depending on solar cycle. In interplanetary space, during the journey to Mars, for example, the dose rate is higher, approximately 300 to 900 millisieverts per year. The current career dose limit for NASA astronauts is set at a level estimated to correspond to no more than a 3% excess lifetime risk of cancer mortality. For a 40-year interstellar mission at dose rates comparable to interplanetary space, the cumulative dose would be approximately 12,000 to 36,000 millisieverts, far exceeding any dose limit considered acceptable and associated with severe and likely fatal radiation sickness well before the journey's end. Shielding can reduce the dose rate, but effective shielding against galactic cosmic rays requires enormous amounts of mass, water, regolith, or other hydrogen-rich materials positioned around the crew habitat. Each kilogram of shielding adds to the spacecraft's total mass, increasing the energy required to accelerate it, compounding the energy problem we already established. Beyond the physical hazards, there is the psychological dimension. Human beings evolved in social groups. We require social interaction for psychological health. We are not designed for small group isolation over multi-decade timescales. The psychological literature on polar expeditions, submarine deployments, isolated research stations, all situations that approximate some aspects of long-duration spaceflight, reveals characteristic patterns of psychological stress, interpersonal conflict, and cognitive degradation that become more severe with increasing duration and increasing isolation. A 40-year journey involves a crew that cannot leave, cannot receive help, cannot be resupplied, and cannot communicate with Earth in real time. Any medical emergency must be handled with on-board resources. Any psychological breakdown must be managed within the group. Any equipment failure must be repaired with on-board spare parts and expertise. This is not the journey of heroes. This is an unprecedented psychological experiment whose outcome over 40 years cannot be predicted from any existing data. Now let us think about what the destination looks like, and why arriving is the beginning of a new set of problems rather than the resolution of the journey's challenges. A starship arrives at Proxima Centauri after 40 years of travel. What does it find? Proxima Centauri is a red dwarf, a star significantly smaller, cooler, and less luminous than our Sun. Its habitable zone, the range of orbital distances at which liquid water could exist on a planet's surface, is very close to the star. Proxima b, the confirmed planet in Proxima Centauri's habitable zone, orbits at approximately 0.05 astronomical units, roughly 1/20th of Earth's distance from our Sun. At this distance, tidal locking is almost certain. The same side of the planet always faces the star, like the Moon always showing the same face to Earth. One hemisphere is in permanent daylight, the other is in permanent night. The temperature difference between the hemispheres drives extreme weather. Proxima Centauri is an active flare star. It produces frequent, intense ultraviolet and X-ray flares, sudden increases in luminosity that drench the habitable zone with high-energy radiation on timescales of minutes to hours. For a planet as close as Proxima b, these flares are severe. The atmospheric sputtering from stellar wind, the gradual stripping of atmospheric gases by the particle radiation from the star, may have depleted any original atmosphere over billions of years. Whether Proxima b is habitable, whether it retains an atmosphere, whether liquid water exists, whether it has anything that would make it a worthwhile destination for a civilization seeking to expand or make contact, is not known. We cannot currently determine this from Earth. Even with the James Webb Space Telescope's most sensitive observations, the characterization of Proxima b's atmosphere remains enormously challenging. The arriving starship would spend its first years discovering whether the enormous energy investment and multi-decade journey has brought it to a barren, airless, radiation-scorched rock orbiting 50 times closer to its star than Earth is to the Sun. This uncertainty, the fact that we do not know what is there before we go, is itself a barrier. Any rational civilization must weigh the probability that a destination is worthwhile against the cost of reaching it. And the cost is so enormous, decades of travel time, planetary energy budgets, the psychological and biological toll on the crew, that the threshold of expected value required to justify the mission is enormous. What could a destination offer that would justify this cost? Contact with another civilization would justify it. If you could confirm that Proxima Centauri hosts a technological civilization before departure, the mission might be worth the cost. But confirmation at interstellar distances requires receiving signals from that civilization, signals that, as we have established, face their own transmission challenges, and that would, by their existence, suggest you could simply communicate electromagnetically rather than undertaking a physical journey. If the destination is known in advance to host another civilization, known because that civilization is broadcasting detectable signals, then physical travel is redundant. You can exchange information electromagnetically. Physical presence adds little to what electromagnetic communication already provides, at a cost many orders of magnitude higher. If the destination is not known in advance to be worthwhile, if you are exploring, then you are making a multi-decade commitment of civilization-scale resources to discover something that may be nothing. The expected value of interstellar physical travel in any realistic assessment is extremely difficult to make positive. Now let us think about a specific numerical comparison that makes the energy barrier visceral in a different way. The total kinetic energy of a 1,000 kilogram spacecraft at 10% of light speed is approximately 4.5 times 10 to the 21st power joules. This is roughly 75% of global annual energy consumption, as we established. But consider what that energy could do alternatively.
75% of global annual energy applied to computing power. At current energy efficiency for computing, and efficiency has been improving rapidly, this energy could run approximately 10 to the 28th power floating point operations. That is 10 octillion operations. For comparison, the total number of synaptic operations in all human brains on Earth for 1 year is approximately 10 to the 24th power, 10 quadrillion. The energy budget of one interstellar spacecraft could power the equivalent of 10,000 human civilizations worth of cognitive activity for a year. Alternatively, 75% of global annual energy applied to building and launching telescopes.
With that energy, you could build and deploy a telescope or array of telescopes with collecting area many orders of magnitude larger than anything currently planned, capable of directly imaging and spectrally characterizing the atmospheres of Earth-like planets around thousands of nearby stars. You could learn vastly more about nearby stellar systems, including whether they host life or intelligence, by spending the equivalent energy on observation rather than on sending a single, tiny spacecraft at 10% of light speed. This comparison illustrates the fundamental economic problem of interstellar physical travel. The same energy that would send a tiny spacecraft to the nearest star at meaningful speed would, alternatively, buy you far more information about the universe through observation. Physical travel is the least efficient way to learn about what is out there. Any civilization sophisticated enough to consider interstellar physical travel is sophisticated enough to recognize this trade-off. And any civilization that has solved the energy problem required for interstellar travel has almost certainly also built the observational infrastructure that makes physical travel largely redundant for the purpose of discovery. The only purposes that physical presence serves, that electromagnetic observation cannot, are the ones that require physical contact: sample collection, terraforming, physical colonization, meeting another civilization in person. But meeting another civilization in person requires first finding that civilization, which is an observational problem, not a travel problem. And once found, the communication problem remains, because two civilizations that find each other across interstellar distances must still negotiate the communication barrier before physical travel can be organized, planned, and justified. Physical interstellar travel is not the first step in making contact. It cannot be. The first step is always electromagnetic, detecting a signal, sending a signal, establishing that something is there. Physical travel, if it follows, is the last step after everything else has been established. And the last step costs more than everything that came before it combined. Now let us think about a specific scenario that crystallizes the problem. The scenario in which two civilizations detect each other's electromagnetic signals and attempt to progress toward physical contact. Civilization A is in the Milky Way at position A. Civilization B is at position B, 1,000 light-years away. A detects a signal from B. The signal carries information, perhaps mathematical sequences suggesting intelligence, perhaps spectral anomalies in B's star consistent with technological activity, perhaps a structured radio transmission. A has confirmed that B exists. A has confirmed that B is at 1,000 light-years. A has confirmed that B was broadcasting 1,000 years ago when the detected signal departed. What A knows about B right now, at this moment, is nothing. The information A has received is 1,000 years old. Whatever B was 1,000 years ago, it may be completely different now. B's civilization may have collapsed. B may have solved all the problems that motivated the signal and moved on to priorities that make further signaling irrelevant. B may have developed in ways that make it unrecognizable compared to what it was when the signal departed. A sends a response. The response will arrive at B 1,000 years from now. Whatever civilization receives that response, if any, will have had 1,000 years of additional development beyond the civilization that originally broadcast the signal A received. If A eventually decides to send a physical mission to B, after decades or centuries of electromagnetic exchange establishing that B exists and is worth visiting, the fastest conceivable mission takes thousands of years. When it arrives, the civilization it finds has had thousands of years of additional development beyond the civilization that was established through the electromagnetic exchange. The mission arrives at a civilization it has never actually communicated with. The civilization it communicated with is thousands of years in the past. The civilization it finds is that civilization's distant descendant, potentially as different from the original as modern humans are from ancient Rome. This is the temporal problem in its most acute form. Physical travel is so slow that by the time any ship arrives at any destination, the conditions that motivated the mission have changed. The civilization that planned the mission is in the past. The civilization that receives it is in the future. The meeting, if it occurs, is between entities that have no direct relationship to the civilizations that initiated the contact. This is not a problem of imperfect technology. It is a consequence of the relationship between the speed of light, the speed of any physical spacecraft, and the timescales of civilizational change. Even if a civilization could travel at 99% of the speed of light, the relationship holds. The only scenario in which it breaks down is if civilizations are so stable, so unchanged over thousands of years, that the civilization that arrives is meeting something recognizably similar to what motivated the journey. And any civilization stable for thousands of years is a civilization so different from any we can conceive of that our models for what it would want, do, or say are not reliable. Now let us think about the specific problem of what we might call civilizational synchrony, the question of whether two civilizations would ever be at compatible stages of development at the same time. Our technological civilization has existed for approximately 300 years in any meaningful sense. Our radio-detectable phase has lasted approximately 120 years. The Sun's remaining main sequence lifetime is approximately 5 billion years. The remaining period during which Earth might be inhabited by a technologically capable civilization, optimistically assuming we solve our current existential challenges, could range from thousands of years to millions of years. If you pick two random moments within the habitable lifetime of any planet and ask whether technological civilizations are present at both moments, the probability depends entirely on what fraction of the planet's habitable lifetime is spent in a technologically capable phase. If Earth's technologically capable phase lasts 10,000 years, an optimistic assumption, then the fraction of Earth's total habitable period spent as a detectable civilization is approximately 10,000 divided by 5 billion, or about 0.00000002, 2 10-millionths of the planet's life. The probability that two planets chosen randomly from the galaxy both happen to be in their technologically capable phase at the same cosmic moment, the same window of time when both can detect and respond to each other's signals, is this fraction squared, approximately 4 times 10 to the minus 14, 4 in 100 trillion. Even if you have billions of potentially habitable planets in the galaxy, the probability that any two of them happen to be simultaneously in their technologically capable window, simultaneously detectable and capable of exchanging signals, is vanishingly small unless the technologically capable phase lasts an astronomically long time. The civilizational synchrony problem is one of the most severe barriers to contact and one of the least discussed.
Even in a galaxy full of civilizations, the probability that two are simultaneously accessible to each other depends on the ratio of their technological lifetime to the galaxy's age. For civilizations with technological lifetimes measured in thousands to millions of years, plausible ranges, the probability of synchrony with any specific other civilization is low. For civilizations with technological lifetimes measured in billions of years, civilizations that somehow persist and remain detectable for comparable timescales to the galaxy's age, the probability of synchrony improves dramatically. But a civilization that persists for billions of years is, by definition, not a civilization like ours. It has solved problems we cannot conceive of. It has developed in ways that make the concept of a civilization as we understand it, a society of biological organisms organized around shared culture and technology, inapplicable. Whatever it is something we do not have language for. The civilizations we can imagine meeting are the ones most like us. The ones most like us are the most likely to face the same existential challenges we face, the ones most likely to end before any meeting can occur. Now let us think about what all these barriers together imply, the sum of the constraints, considered as a system rather than individually. The distance barrier. Stars are separated by light years. Physical travel at any achievable velocity takes tens of thousands to millions of years per journey. The nearest star is already out of reach at current technology. The energy barrier. Achieving any velocity fraction of light speed requires planetary-scale energy budgets. The rocket equation compounds with increasing velocity.
No civilization confined to a single planet can plausibly power interstellar physical travel. The biological barrier. Organisms evolved for planetary surfaces are fragile in space. Radiation, microgravity, psychological stress, and the absence of resupply degrade biological systems over the timescales of any interstellar journey. Shielding adds mass, which multiplies the energy requirement. The communication barrier. Electromagnetic signals, the fastest possible medium for exchanging information, travel at light speed. Round-trip communication times to nearby stars are measured in years. To typical galactic distances, thousands to hundreds of thousands of years. Interactive conversation is essentially impossible.
The temporal barrier. The time required for physical travel means that any arriving mission encounters a civilization that has had thousands to millions of years of additional development beyond the civilization that was characterized during the pre-departure observation phase. The mission arrives in the future of the world it was sent to meet. The synchrony barrier. Two civilizations must exist in technologically capable phases simultaneously, must be broadcasting and capable of receiving at the same cosmic moment for any contact to initiate. The probability of this synchrony for civilizations with finite technological lifetimes is extremely small. Each of these barriers is individually severe. Together, they are not additive, they are multiplicative. You must overcome all of them simultaneously. Solving the energy problem does not solve the biological problem. Solving the biological problem does not solve the temporal problem.
Solving the temporal problem does not solve the synchrony problem. The probability of meeting of two civilizations from different stellar systems being in physical contact is the product of the probabilities of overcoming each individual barrier. If each barrier has even a 10% probability of being overcome, the combined probability is 10% raised to the power of the number of barriers. For 6 barriers, approximately 0.000001%. These are not carefully calibrated numbers. They are illustrations of how compounding constraints work. The point is that the universe has arranged multiple independent barriers, each individually severe, each rooted in fundamental physics rather than engineering limitations, that must all be simultaneously overcome for any meeting to occur. This is not pessimism. It is the physics of the universe applied to the specific problem of civilizations meeting across interstellar space.
The universe has built a system of barriers that approaches impossibility, not from malice, not by design, but as a consequence of the specific values of the physical constants. the speed of light, the inverse square law, the thermodynamics of living systems, and the specific geometry of the universe, the distances between stars, the age of civilizations relative to the age of the cosmos. The universe makes civilizational meetings essentially impossible because the universe was not built for civilizational meetings. It was built for physics. And physics happens to make meeting very, very hard. Let us now think about something that the previous analysis has established as a framework, but has not yet applied to its most interesting specific cases. The question of what the barriers look like when you examine not the typical scenario, but the most favorable possible scenarios. Because the most compelling argument for impossibility is not that the average case is hopeless. The average case is obviously hopeless. The average distance between stars in the galaxy is several light years. The average civilizational lifetime is unknown, but probably short. The average energy budget of a planetary civilization is insufficient for interstellar travel. The compelling argument is that even the best case, the scenario designed to be as favorable as possible to the possibility of meeting, is still essentially impossible. Let us build the best case. Two civilizations, close together, the nearest possible stellar neighbors. Let us say 4.24 light-years apart, the distance from Earth to Proxima Centauri. Both civilizations are long-lived. They have survived their technological adolescence, avoided self-destruction, and maintained technologically capable societies for millions of years. Both have solved the energy problem. They have access to stellar-scale energy through Dyson sphere equivalent technology. Both civilizations are broadcasting detectable signals. They have been doing so for millions of years. Both are listening. They have devoted enormous resources to detecting signals from other civilizations. Both happen to exist at the same cosmic moment. The synchrony problem is solved by their extraordinary longevity. These are the most favorable possible starting conditions. Every barrier that can reasonably be specified as solvable has been solved. We are giving the meeting every possible advantage. What happens? Civilization A detects Civilization B's signal. 4.24 years after B sent it, A receives it. A confirms. There is a civilization at Proxima Centauri. It is broadcasting. It has been doing so for the period of observation. A responds. 4.24 years after A sends its response, B receives it. Electromagnetic contact is established. Round-trip communication, 8.48 years per exchange. Over the next few hundred years, A and B exchange information. They learn each other's languages, a process that requires many exchanges, each taking 8.48 years. They share science, mathematics, culture, history. This electromagnetic dialogue is genuinely productive. Both civilizations learn things they could not have learned from observation alone. This is the good part. This works. Electromagnetic contact between civilizations 4.24 light-years apart is physically possible, requires no new physics, and is consistent with everything we know. Now, physical contact. Can A send representatives to B or vice versa? Even in the best case, civilizations with stellar-scale energy budgets, the constraints remain. The energy required to send a crewed spacecraft from A to B at 99% of the speed of light is enormous. Even with a Dyson sphere producing 3.86 times 10 to the 26th power watts, the energy to accelerate a meaningful crewed spacecraft to 99% of light speed requires many months to years of the star's full output, devoted entirely to this purpose. This is a significant but not prohibitive expenditure for a civilization with Dyson sphere-level energy access. Assuming the energy is available, the ship departs. At 99% of the speed of light, the journey takes approximately 4.28 years in the external frame, and approximately 7 months in the crew's subjective frame. After 4.28 years, during which the electromagnetic dialogue has continued, so B knows A is coming, the ship arrives. The crew arrives at B,
They are greeted by B. Physical contact has occurred. This is the best case, and it is not impossible. Under the specific conditions described, two long-lived civilizations with stellar-scale energy at the nearest possible stellar separation, physical contact is achievable. The journey is expensive, the communication is slow, the temporal challenges are manageable given the civilization's extraordinary longevity. But notice what has been required to make this possible. Civilizational lifetimes of millions of years. This is an assumption so extraordinary that it warrants examination. Our own civilization has existed for approximately 300 years in its technologically capable form. Maintaining a civilization that is technologically capable and coherently organized for millions of years across the inevitable changes in culture, governance, values, technology, and population that any society undergoes has no historical precedent at any scale. The longest continuous civilizational traditions on Earth span a few thousand years, with enormous changes throughout. A million-year civilization is not a civilization in any sense we have experience with. Stellar-scale energy. Building a Dyson sphere, or any technology that captures the full energy output of a star, requires first solving the problem of manufacturing and deploying a structure with a surface area approximately 600 million times that of Earth. The material and manufacturing challenges of this engineering are staggering.
We have no prototype, no theoretical roadmap, no physical demonstration that this is achievable. It is physically consistent with known laws, but the distance from our current capability to this capability is incomprehensibly large. Electromagnetic synchrony maintained for the duration. For A and B to detect each other's signals, both must be broadcasting in detectable ways at the same time. For civilizations 4.24 light-years apart, this requires both to have been broadcasting for at least 4.24 years simultaneously. This is trivially achievable for any long-lived civilization, but it depends on both civilizations broadcasting in the same direction, or more realistically, in all directions, and both listening in the right frequency ranges at the right times. SETI has been listening for 65 years. We have found nothing. The synchrony of listening and broadcasting across all directions and all frequencies simultaneously is itself a resource-intensive undertaking. Even in the best case, the case specifically designed to be as favorable as possible to the possibility of meeting, the conditions required to make it work involve assumptions so extreme that they may represent an impossible bar. Now let us think about the best case for the average scenario. Not the nearest neighbours, but typical galactic separations. The average distance between stars in the Milky Way is approximately 5 light-years. But the typical distance from any given star to any other civilizational hosting star, assuming civilizations are rare, as the Fermi paradox suggests, is much larger. If there are 1,000 technologically capable civilizations in the Milky Way at any given moment, an optimistic assumption given the silence of the universe, the average distance between any two of them is approximately 1,000 light-years. At 1,000 light-years, the round-trip communication time is 2,000 years. The journey time at 99% of light speed is approximately 1,010 years in the external frame. The subjective time is approximately 143 years, longer than a human lifetime. A civilization that sends a crew on a 143-year subjective journey is sending people who will age from youth to old age and die during the transit. Any children born during the journey will arrive at the destination as adults who have never known a planet. The crew that arrives is not the crew that departed in any meaningful social or cultural sense. It is a generation removed from the civilization that built the ship. The civilization that receives this mission is not the civilization that sent the confirming signal 1,000 years before the ship departed. It is 1,000 years further evolved, in ways that could be as dramatic as the difference between ancient Rome and the present day, or more dramatic. The mission, conceived as a meeting between two specific civilizations at specific moments in their development, arrives to find something 2,000 years away from the civilization it was meant to meet. The meeting, if it occurs, is between versions of both civilizations that had no direct contact with the decision-making that sent the mission. This is not a meeting, it is an archaeological expedition arriving at a living culture, one that has moved on while the archaeologists were in transit. Now let us think about something that is specific and under-discussed: the economic argument against interstellar physical contact applied to a civilization sophisticated enough to be genuinely considering it. Any civilization capable of interstellar travel, with stellar-scale energy, long civilizational lifetimes, advanced material science, has enormous resources. But resources are still finite. Every resource devoted to sending a physical mission to another star is a resource not devoted to other uses. What are the opportunity costs of an interstellar mission? The same energy budget devoted to computation could power a level of information processing that effectively simulates all possible outcomes of the mission and more. A civilization with Dyson sphere energy and advanced computing could, in principle, model the receiving civilization's likely state on arrival with enough accuracy to make the physical trip largely redundant. The same energy budget devoted to telescopy could build observatories capable of characterizing the atmospheres, surfaces, and even some features of the surfaces of planets at 1,000 light-years, with resolutions that may not require physical presence to achieve many scientific goals. The same energy budget devoted to self-improvement, building more sophisticated infrastructure, solving problems within their own stellar system, expanding their own capabilities, might produce more civilizational benefit than the encounter. The decision to send a physical interstellar mission is a decision to prioritize one specific kind of interaction, physical contact with another civilization, over an enormous range of alternatives. And for a civilization sophisticated enough to seriously consider this decision, the alternatives are genuinely extraordinary. This is the economic argument for why, even in the best case, physical interstellar contact may not occur. It is not that it is impossible, it is that the opportunity cost is enormous, and the benefit is achievable through cheaper means, primarily electromagnetic exchange. Any information that can be transmitted physically can also be transmitted electromagnetically. The physical presence of a representative from Civilization A at Civilization B's planet adds what, exactly, that years of electromagnetic exchange cannot provide? Physical samples, material objects that cannot be transmitted electromagnetically. This is genuinely valuable scientifically. But the scientific value of a physical sample from another stellar system, while immense, must be weighed against the cost of obtaining it. Physical interaction with the environment, landing, exploring, collecting. This requires not just the transit of crew, but the infrastructure for surface operations, the resources for the return journey, the full commitment of a manned mission rather than a probe. A relationship that transcends electromagnetic exchange, something about physical presence, about being in the same place, that adds value beyond what information exchange provides. This is the most compelling argument and the hardest to quantify. There is something about physical presence that electromagnetic contact cannot replicate. The full sensory experience of sharing space, the ability to interact in real time without communication delays, the symbolic weight of actual travel. But this argument, the value of physical presence, is most compelling to biological organisms with evolved social instincts. Organisms whose entire evolutionary history was conducted in physical proximity,
who have instincts calibrated for face-to-face interaction, who derive social and psychological value from physical presence in ways that are deep and non-rational. Whether these instincts survive 1 billion years of civilizational development, whether a civilization millions of years old still values physical presence in the way that drives humans to travel to distant places simply to be there, is genuinely uncertain.
A civilization that has had millions of years to examine and modify its own psychology might have values and motivations utterly different from the ones that would make physical interstellar contact feel important. Now let us think about the concept of the Great Filter, the idea that somewhere in the progression from simple chemistry to interstellar civilization, there is a filter that most potential civilizations never pass. The Great Filter argument, developed by economist Robin Hanson, runs as follows. If interstellar civilizations were common, we would expect to see their signatures throughout the universe. We see nothing. Therefore, something filters out most potential interstellar civilizations before they become detectable. This filter could be in our past. The development of life, complex life, or intelligence might be so rare that we are among the only civilizations. Or in our future, perhaps all civilizations self-destruct before becoming interstellar. The barriers we have been discussing are not the Great Filter in the Hansen sense. They are not barriers that destroy civilizations. They are barriers that prevent civilizations from meeting each other, even if both exist. But they are relevant to the filter discussion in a different way. The universe's barriers to interstellar contact suggest that even in the absence of any self-destruction tendency, civilizations would not meet. Even a galaxy full of thriving, long-lived civilizations would not produce observable signatures of widespread physical contact, because physical contact between stellar systems is too expensive, too slow, and too temporally challenging to be a common occurrence. This means that the Fermi paradox, the absence of observable signatures of civilizations, has a natural explanation that does not require a great filter in the catastrophic sense. Civilizations are not observed because they cannot reach each other to produce the kind of coordinated, galaxy-spanning signatures that would be most observable. Each civilization is an island. Each island is isolated by the barriers we have described. The islands may be thriving, may be extraordinarily rich and complex internally, but their isolation from each other is enforced by the physics of the universe. The Fermi paradox in this interpretation is not evidence that civilizations are rare or that they destroy themselves. It is evidence that the universe has built barriers sufficient to prevent civilizations from meeting, barriers that are so effective that even a galaxy full of long-lived civilizations would appear silent. Now let us think about what recent scientific developments have added to this picture, specifically the growing understanding of exoplanet atmospheres and what it implies for the future of contact. James Webb Space Telescope is currently conducting the first serious characterization of exoplanet atmospheres. It has detected carbon dioxide in the atmosphere of WASP 39b. It has measured the thermal emission from TRAPPIST-1 planets. It has produced preliminary spectra of sub-Neptune worlds in habitable zones. The detection of potential biosignatures, oxygen, methane, ozone in biologically significant combinations, is within the capability of Webb and its successors for nearby star systems. This observational capability is relevant to the meeting problem in a specific way. If we can characterize the atmospheres of nearby exoplanets, if we can detect biosignatures at distances of a few to a few tens of light years, we can potentially establish that life exists at another star without any physical contact. And if we can detect biosignatures, we can eventually detect technosignatures, atmospheric compositions consistent with industrial activity, electromagnetic leakage, structured laser signals. The detection of technological civilization at another star does not require physical presence. It requires sufficiently sensitive instruments. The meeting problem, framed as the challenge of knowing whether another civilization exists, may be solved not by physical travel, but by observational astronomy. And here the specific barriers reassert themselves. Because knowing another civilization exists is not the same as meeting it. Knowing is electromagnetic, it happens at the speed of light, limited by our instrument sensitivity, achievable within decades to centuries for nearby civilizations. Meeting, physical contact, is still governed by all the barriers we have described. The detection of a biosignature at Proxima Centauri tells us there is something there. It does not allow us to shake hands with it, or exchange physical samples, or inhabit the same space at the same moment. The gap between knowing and meeting is the gap between electromagnetic observation and physical travel. It is the gap between what the universe permits easily and what the universe makes essentially impossible. Future observatories, the Habitable Worlds Observatory planned for the 2040s and whatever follows it, will characterize dozens to hundreds of nearby stellar systems in sufficient detail to detect signs of life or technology. We may, within this century, know that other civilizations exist. We will not be able to meet them.
The knowledge and the contact are separated by the full weight of the barriers we have discussed, by 4.24 light-years to the nearest case, by tens to thousands of light-years for any broader sample, by energy requirements that dwarf our current capabilities, by biological constraints that no technology has yet overcome, by temporal problems that no speed can fully solve. Knowing they are there and being unable to go is a specific kind of situation. It is the situation the universe is arranging for us, and if the barriers apply equally to all civilizations, as physics dictates they must, for every civilization everywhere. Every civilization that develops sufficient observational capability will know there are others, and essentially no civilization will be able to physically meet those others. The universe appears to have specifically arranged this outcome, not by design, but by the specific values of its physical constants and the specific geometry of stellar distributions. It has built sensors capable of detecting across light years, while simultaneously building barriers that prevent crossing those light years. The universe shows civilizations each other. The universe prevents civilizations from reaching each other. This is the specific cruelty, if cruelty is the right word for an outcome of physics rather than intention, that the universe has arranged. Now let us think about whether anything could change this picture, whether any development within physics or technology could genuinely overcome the barriers. Faster-than-light travel is the obvious candidate. If the speed of light barrier were circumvented, if some form of travel allowed physical objects to cross stellar distances faster than light, the distance and temporal barriers would be dramatically reduced. The candidates for faster-than-light travel from theoretical physics are well known. The Alcubierre warp drive, a solution to general relativity's field equations that describes a space-time bubble moving faster than light relative to the surrounding space. Wormholes, topological shortcuts through space-time connecting distant regions. Higher dimensional travel, shortcuts through spatial dimensions not accessible at everyday scales. Each of these is a mathematical structure that appears in theoretical physics. None has been physically demonstrated. None has been shown to be constructible. Each faces specific physical objections that may be fundamental rather than engineering challenges. The Alcubierre drive requires negative energy density, a form of exotic matter with no macroscopic physical demonstration. The amount required in original calculations was comparable to the mass energy of Jupiter in negative form. More recent refinements have reduced this requirement, but negative energy density at macroscopic scales remains purely theoretical. Additionally, the Alcubierre drive appears to violate causality under some analyses, allowing information to travel backward in time, which produces logical paradoxes that most physicists consider indicative of a fundamental physical prohibition. Wormholes require exotic matter to hold them open against collapse. Traversable wormholes, large enough for physical passage, have no known natural analogue. Constructing one, if it is possible at all,
would require engineering at scales that dwarf even the Dyson sphere challenge. Higher dimensional travel requires that the additional spatial dimensions of string theory be both accessible and navigable, neither of which has any observational support or theoretical demonstration.
The honest assessment: faster-than-light travel is physically permitted by some theoretical structures, but the physical requirements for implementing any of these structures are either currently unknown, likely impossible under known physics, or require exotic matter whose existence is not established. If faster-than-light travel is impossible, and most physicists believe it is, for reasons rooted in causality conservation, then the distance barrier is permanent, the temporal barrier is permanent, and the energy barrier can only be reduced, not eliminated. If faster-than-light travel is possible in some form not yet discovered, if future physics reveals some mechanism that makes stellar distances crossable in humanly relevant timescales, then the meeting problem becomes dramatically easier. But this possibility is not a scientific expectation. It is a hope based on the incompleteness of our current physical understanding. Betting on future physics to solve the meeting problem is betting that our current understanding of the universe, which has been extraordinarily successful at characterizing reality across many orders of magnitude in scale and energy, is wrong in exactly the way needed to make interstellar travel feasible. This cannot be ruled out, but it cannot be relied upon. Now let us think about a specific alternative that is physically grounded and does not require new physics: the information-centric model of interstellar contact. If physical travel is essentially impossible and electromagnetic communication is feasible, the obvious question is, what can two civilizations actually accomplish through electromagnetic exchange alone? The answer, perhaps surprisingly, is enormous. Two civilizations that have established electromagnetic contact can exchange the full content of their scientific knowledge. They can share mathematical structures, physical theories, biological data, historical records, cultural artifacts, in any medium that can be digitized, technological designs, philosophical frameworks, and any other information that can be encoded in an electromagnetic signal. The rate of this exchange is limited by the bandwidth of the signal and the encoding efficiency. But for civilizations with Dyson sphere energy budgets and advanced communication technology, the achievable bandwidth is immense. The total information content of all human knowledge, every book ever written, every scientific paper, every cultural artifact in digital form, is estimated at a few tens of exabytes. This could be transmitted to Proxima Centauri at a rate corresponding to even modest laser communication capability in a matter of hours to days. The full scientific and cultural content of a civilization could be exchanged in the first few years of electromagnetic contact. What follows is not an exchange of stored information, but an ongoing exchange of developing knowledge, each civilization contributing its current understanding to an evolving dialogue with 8.48-year round-trip lag. This is not nothing. This is, in many ways, more than physical contact could provide. Physical contact between two civilizations, however dramatic the symbolism, is limited to the physical presence of a finite number of individuals. Electromagnetic contact between two civilizations allows the full intellectual and cultural output of both civilizations to be available to the other. The question is whether this suffices, whether electromagnetic exchange, rich, comprehensive, continuous, can be a substitute for physical presence. For certain purposes, clearly yes. For scientific exchange, for cultural understanding, for the accumulation of knowledge that would otherwise take each civilization individually much longer to develop, electromagnetic exchange is a complete substitute for physical presence. For other purposes, the question is more complex. The experience of physical presence, the full sensory richness of being in the same location, the ability to interact in real time without delay, the symbolic weight of actual travel and arrival,
These are things that electromagnetic exchange cannot replicate. Whether these things matter, whether they are necessary for a relationship between civilizations to be meaningful, depends on the values and psychology of the civilizations involved. For a civilization whose members are biological organisms with evolved social instincts calibrated for face-to-face interaction, physical presence might be deeply important.
For a civilization that has had millions of years to revise its own psychology and values, physical presence might be considered valuable, but not necessary. The universe, by making physical contact essentially impossible and electromagnetic contact feasible, has made a specific choice about what kind of contact between civilizations is possible. It has made the informational contact easy and the physical contact hard. Whether this is sufficient, whether civilizations that have exchanged all their knowledge and culture but never shared physical space have truly met, is not a question physics can answer. It is a question about what meeting means. And the answer to that question is different for different civilizations at different stages of development, with different values and different histories. The universe makes physical meeting essentially impossible. It makes informational meeting relatively easy.
Whether the latter substitutes for the former is left to the civilizations to decide. Now let us think about what all of this means for the specific situation we are in. A civilization that has been technologically capable for 300 years, that has been broadcasting for 120, that has detected no response, and that is now developing the instruments to characterize the atmospheres of nearby exoplanets. We are at a specific transition point. For the first 120 years of our electromagnetic detectable phase, we have been broadcasting without the observational capability to detect biosignatures or technosignatures at other stars. We announced our presence before we had the means to look for anyone else's. Now, with James Webb Space Telescope and its successors, we are developing for the first time the observational capability to actually look for signatures of life at nearby stars. We are at the beginning of the era when we might actually detect something.
If we do detect something, if the next generation of telescopes identifies a biosignature at a nearby star, we will face the problem we have been discussing tonight in its most acute form. We will know that something exists there. We will be unable to go there in any time frame relevant to our civilization. We will be able to communicate electromagnetically with a delay of years to decades depending on the distance. We will be unable to confirm whether the biosignature represents simple life or complex life or intelligence. The detection of a biosignature is not the detection of a civilization. It is the detection of biology, which on Earth has existed for 3.8 billion years, only recently producing anything detectable from light years away. A biosignature at Proxima Centauri tells us chemistry is happening that is consistent with life. It does not tell us whether that life has language, technology, or any awareness of us. And even if it is intelligent, even if the biosignature is accompanied by technosignatures that confirm technology, the barriers remain. We know they are there. We can talk to them, slowly. We cannot go. This is the situation the universe appears to be arranging for us. The situation it has arranged, by physics, for every civilization that develops observational capability. A universe of civilizations that can see each other across the void and cannot cross it. Connected by light, separated by everything else. Let us now think about something that follows from the analysis, but has not been made explicit. The specific question of what the barriers mean for the long-term future of intelligence in the universe, and whether the physical isolation of civilizations from each other has consequences for the universe's ultimate trajectory. This is not a speculative excursion. It follows directly from the physics. The universe contains, or has contained, or will contain, an enormous amount of organized complexity. Stars, planets, chemical systems, biological systems, potentially minds. This organized complexity is the result of 13.8 billion years of the universe doing what physics requires. Matter organizing itself under the influence of gravity, electromagnetic force, and the arrow of time driven by thermodynamics. If civilizations are common, if the universe produces minds in abundance, then the universe contains, at various points in its history, an enormous wealth of knowledge and culture and understanding. Each civilization independently discovering mathematics, physics, chemistry, biology. Each independently developing the capacity to understand the cosmos. Each independently building models of the universe that are accurate and detailed.
This parallel development of understanding, this situation in which many minds independently reach similar conclusions about the nature of reality, would be one of the most remarkable features of the universe if it obtains. And all of it is isolated from all the rest. Each civilization's knowledge and culture and understanding exists only within that civilization's stellar neighborhood. It cannot escape, or can escape only at light speed in all directions, gradually weakening with the inverse square law, eventually becoming undetectable above the noise of the universe's background. When a civilization ends, whether through natural stellar evolution, self-destruction, or the simple statistical inevitability of finite lifetimes, its accumulated knowledge is lost to the rest of the universe. The mathematics they derived, the physics they discovered, the art they created, the history they experienced, the specific understanding they built of the universe from their particular vantage point in it. All of it either dissipates into the electromagnetic background or is preserved in forms too faint and too distant to be retrieved. The universe is accumulating, losing, and reaccumulating knowledge independently in millions or billions of isolated locations. Each civilization reinventing the wheel, or its cosmic equivalent, because the wheel invented by every previous civilization is inaccessible across the distances the universe imposes. This is not an efficient way to accumulate understanding. It is the opposite, a maximally inefficient system in which each location must start from scratch, in which no knowledge transfer between civilizations is possible except the trickle that electromagnetic exchange across light years allows, in which the loss rate of accumulated knowledge is high and the preservation rate is low.
The universe, from the perspective of knowledge accumulation, is structured like a collection of isolated laboratories, each conducting similar experiments in parallel, unable to share results, unable to build on each other's work, unable to avoid reinventing things that have already been discovered 1,000 light years away. This is one of the most poignant implications of the meeting barriers. Not that civilizations cannot share physical space, but that they cannot share accumulated wisdom across the timescales and distances that the universe imposes. Now let us think about a specific calculation that puts the electromagnetic isolation in quantitative terms. Our civilization has been broadcasting electromagnetic signals for approximately 120 years. Our electromagnetic sphere, the region of space from which our signals are detectable, has a radius of 120 light years. The Milky Way has a diameter of 100,000 light years. Our electromagnetic sphere covers a volume of approximately 4/3 pi times 120 cubed light years cubed, is approximately 7.2 million cubic light years. The volume of the Milky Way's habitable disk, the region where stars capable of hosting life are concentrated, is approximately 4/3 pi times 50,000 cubed cubic light years, is approximately 5.2 times 10 to the 14th power cubic light years. Our electromagnetic sphere represents approximately 0.00000014% of the Milky Way's habitable volume. In terms of fractional galactic coverage, after 120 years of broadcasting at the speed of light, our electromagnetic footprint covers roughly 1/1,000,000% of our galaxy. At this rate, expanding at light speed in all directions, Our electromagnetic sphere will cover half the Milky Way in approximately 50,000 years. It will cover the full galaxy in approximately 100,000 years. 100,000 years is not a long time cosmically, but it is approximately 14 times the span of recorded human history.
No institution, no culture, no civilization has maintained continuity over 100,000 years. The question of whether our civilization, or any successor civilization, will still be broadcasting in 100,000 years is deeply uncertain. And even if our signals do reach every corner of the galaxy in 100,000 years, any civilization that receives them is receiving signals from 100,000 years in our past. The civilization that receives our signals at the far edge of the galaxy will not know whether we still exist. They will know whether we existed 100,000 years before their moment of reception. Now let us think about the specific question of what electromagnetic exchange between civilizations can and cannot accomplish, because this is the most realistic form that any contact will take, and it deserves more careful analysis than it usually receives. Two civilizations exchanging electromagnetic signals across stellar distances can share information.
They can share any information that can be encoded in a signal, which is essentially all information, since information is substrate independent and can be encoded in electromagnetic carrier waves. But the exchange has specific structural limitations that physical presence does not. The first limitation is latency. Every exchange has a round-trip delay equal to twice the light travel time between the civilizations. At 4.24 light years, this is 8.48 years. At 100 light years, it is 200 years. At 1,000 light years, it is 2,000 years. What this latency means in practice is that electromagnetic exchange between distant civilizations is not conversation. It is correspondence, the exchange of complete, self-contained messages, each designed to be understood without real-time feedback. The dialogue that develops is the slowest possible form of intellectual exchange. Each party must wait years to decades to centuries before knowing whether the previous message was understood, before being able to ask a clarifying question, before being able to correct a misunderstanding. This dramatically limits the kind of collaborative intellectual work that can occur between civilizations via electromagnetic exchange. Complex technical collaborations, the joint development of new technology, joint scientific investigation of specific questions, require rapid iteration. Questions, answers, corrections, refinements, the back and forth that produces new understanding. With latency measured in decades, this iteration is essentially impossible. What remains possible is the transmission of complete, finished knowledge, everything a civilization has already worked out. The results of science already established, the products of culture already created, the history already accumulated. This is enormously valuable. But it is fundamentally different from collaborative discovery, from the joint production of knowledge that physical proximity enables. Two civilizations exchanging electromagnetic signals can each learn everything the other already knows. They cannot easily discover new things together. The latency prevents the collaborative process that joint discovery requires. The second limitation is authenticity. Any electromagnetic signal can be fabricated. A signal claiming to represent a civilization at a given star could be a natural phenomenon misidentified, an artifact of the transmission medium, or, in a scenario involving civilizations with potentially adversarial relationships, a deliberate deception. Verifying the authenticity of a claimed signal from another civilization is extraordinarily difficult across stellar distances. Physical presence allows direct verification. You can see the civilization, interact with it, collect physical evidence of its existence. Electromagnetic exchange requires trusting the signal with limited ability to cross-check against physical evidence. The third limitation is the directionality problem. Electromagnetic signals disperse in all directions.
To be received at a specific target, a signal must either be broadcast in all directions, which dilutes it rapidly with distance, or be aimed at a specific target. Aimed signals require knowing where to aim, which requires prior knowledge of the target's location that may not be available before contact is established. And establishing contact in the first place requires that both parties are broadcasting in the right direction at the right time, or that one is broadcasting in all directions and the other is listening carefully enough in the right direction at the right frequency. SETI has been listening for 65 years, examining tens of thousands of stellar systems, covering a range of frequencies from megahertz to gigahertz, without a confirmed detection. This is either because civilizations are rare, or because they are broadcasting in ways we have not yet identified, or because the specific problem of establishing first contact, of breaking the silence, is harder than it appears. The first message problem is analogous to the two-party problem in cryptography. Two parties want to establish secure communication, but they have never communicated before and have no shared secret. How do they bootstrap? For civilizations separated by light years, the bootstrapping problem is extraordinarily difficult. You need to broadcast in all directions across all frequencies for an indefinite period, hoping that someone is listening in the right place at the right time. The universe provides no obvious coordination mechanism. There is no agreed upon frequency for first contact, no agreed upon direction, no agreed upon timing. Any such agreement would have to be established without any prior communication, which is the very problem to be solved. Now let us think about something that connects the meeting barriers to a question that philosophy and science have circled for decades: the question of whether consciousness, or mind more broadly, has any special relationship to the structure of the universe. The universe has produced minds. Regardless of how rare or common this is, the fact that it has happened at least once, here on Earth, is established. Minds capable of modeling the universe from within it. Minds capable of asking why civilizations cannot meet and what the universe has done to prevent it. There is no obvious reason from the fundamental laws of physics why minds should exist. The laws of physics, quantum mechanics, general relativity, the standard model of particle physics, describe a universe of fields and particles following deterministic or probabilistic rules. These rules produce stars and planets and chemical systems. Whether they produce minds depends on additional circumstances, chemistry, planetary conditions, evolutionary processes that are not uniquely specified by the fundamental laws. The universe might have been physically identical in its fundamental laws and produced no minds. It might have produced only mindless chemistry. The production of minds is a contingent outcome of specific conditions applied to the fundamental laws, not an inevitable consequence of those laws. And yet minds exist. And those minds find themselves in a universe that, at the scales relevant to their meeting each other, is built to prevent it. As if the universe produced minds and then immediately separated them with barriers that approach impossibility. This observation has no explanatory content. It does not tell us why the universe is this way, or whether it could have been otherwise, or whether there is any purpose to the arrangement. The laws of physics that produce the barriers also produce the minds that notice the barriers, the same physics. But it is remarkable, as an observation, that the scales of the barriers so precisely match the scales of mind production. Minds arise on planetary surfaces around individual stars. The barriers are at the interstellar scale, precisely the scale between individual stellar systems. The minds arise at exactly the scale at which the barriers become operative. This is not a designed feature of the universe. It is a consequence of the fact that the conditions for mind production, stable stellar systems, liquid water, long timescales for evolution, are local, planetary scale conditions, while the structure of the universe, the distances between stars, the speed of light, the energy requirements for interstellar travel, operates at stellar and galactic scales. The universe is built so that the unit of mind production is the planetary system, and the unit of isolation is also the planetary system. Each planet, potentially a world of minds,
each world isolated from every other by the barriers we have described. This coincidence, if it is a coincidence, means that mind is, by the physics of its production, a local phenomenon, confined to the planetary scale in which it arose, unable to extend itself to the stellar scale at which contact might occur. Whether this arrangement is fortunate or unfortunate for the minds it produces depends on what you value. Isolation means independence. Each civilization developing its own unique understanding, its own culture, its own relationship with the cosmos, without the homogenizing influence of contact with other civilizations. Isolation also means loneliness, the knowledge that others may exist, and the inability to know them, to learn from them, to share with them. The universe has arranged for both the independence and the loneliness. It has not arranged for the meeting. Now let us think about something that is rarely considered in discussions of the Fermi paradox and the meeting barriers: the possibility that the barriers are not symmetric. We have been assuming that any civilization anywhere faces the same barriers to interstellar contact that we do. This is true in terms of the fundamental physics, the speed of light, the rocket equation, the energy requirements of interstellar travel. These apply equally to any physical system anywhere in the universe. But the practical implications of the barriers depend on the specific circumstances of each civilization, their energy budget, their technology, their longevity, their location in the galaxy. A civilization near the center of the galaxy, where stellar density is much higher than in our location in the outer disk, faces shorter interstellar distances. The average distance between stars near the galactic center is perhaps 0.1 to 0.5 light-years, compared to the several light-years typical in our neighborhood. A civilization in a dense stellar environment has neighbors a factor of 10 to 50 times closer than our nearest neighbors. This changes the energy requirements for interstellar travel substantially. At 10% of the stellar density difference, the energy required for a round trip to the nearest neighbor drops by a factor of 100. The communication latency drops by the same factor. The temporal barriers are dramatically reduced. A civilization near the galactic center might find interstellar physical travel more feasible. Not easy by any measure, but less astronomically expensive than a civilization in our relatively sparse outer disk location. Similarly, a civilization around a red dwarf star, the most common stellar type in the galaxy, in a dense stellar neighborhood, might have many red dwarf neighbors at distances of a light year or less. Red dwarfs have extremely long lifetimes, trillions of years for the smallest, providing enormous time for civilizations to develop and potentially for interstellar exchange to occur over geological timescales, even at low travel speeds. In these more favorable environments, the barriers are reduced but not eliminated. The fundamental physics is the same. The energy requirements are lower by factors of hundreds, but still enormous. The temporal barriers are reduced, but not removed. The conclusion holds for any plausible physical environment in the universe. Interstellar physical contact between biological civilizations is at the extreme limit of physical possibility, achievable only under the most favorable conditions and with the most extraordinary civilizational commitments. But the conclusion is not uniform. Some civilizations face worse barriers than others, and the most favorable circumstances might represent cases where physical contact genuinely occurs. A galaxy of billions of civilizations, each isolated from all but its immediate stellar neighbors, with occasional physical contact between civilizations in densely packed stellar environments, and electromagnetic exchange providing the primary connection across larger distances, this is a plausible picture of what a universe full of intelligence looks like. Not the science fiction image of an interstellar community with regular travel between stars and meetings between diverse civilizations. A more isolated, quieter picture. Many civilizations, mostly unknown to each other, each developing independently, occasionally exchanging information electromagnetically across the gaps that physics makes largely uncrossable. This picture is consistent with the Fermi paradox, consistent with the silence of the universe, without requiring that civilizations are rare or that they destroy themselves. It requires only that the physics of the universe is exactly what we have described. Barriers to physical meeting that are severe, compounding, and grounded in fundamental physical law. Now let us think about something that gives the barriers a specific personal dimension, the question of what they mean for us, specifically, right now, in the first decades of our observable universe. We are in a specific historical moment. We have been technologically capable of detecting electromagnetic signals from other civilizations for approximately 65 years, the duration of organized SETI. We have been broadcasting in ways potentially detectable from nearby stars for approximately 120 years. We are now developing for the first time instruments capable of detecting the atmospheric signatures of life on nearby exoplanets. This is an unrepeatable moment in our civilization's history, the moment when the question of whether we are alone in the universe transitions from philosophy to science. When detection becomes genuinely possible in principle with achievable instruments. The specific stakes of this moment are clarified by the barriers we have described. If we detect a biosignature, evidence of biology at a nearby star, we will know something of enormous significance. But we will face the full weight of the barriers immediately. We cannot go there. Not in any time frame our civilization will survive, unless our civilization persists for tens of thousands of years and develops energy access we cannot currently conceive. We can communicate, slowly, with delays of years to decades, without the ability to verify anything through physical presence, without the ability to ask and receive answers on any timescale relevant to individual human lives. We can know they are there. We can learn their science and culture and history, or share ours, across decades and centuries of electromagnetic exchange. We can understand something about what life looks like at another star without ever sharing physical space with it. This is the actual prospect that the universe offers. Not the meeting of science fiction, the dramatic handshake, the exchange of technology, the transformation of both civilizations through direct contact, the slower, quieter, deeply strange connection of civilizations exchanging light across the void, knowing of each other's existence without ever occupying the same place. And even the electromagnetic exchange, requires that the other civilization is broadcasting, that we are listening at the right frequency, that the timing works out, that both civilizations survive long enough to conduct any meaningful exchange. The universe does not guarantee any of this. It provides the physical possibility of electromagnetic contact and erects near physical impossibility against physical contact. What falls in between, whether the electromagnetic exchange actually occurs, whether the timing and the frequencies and the longevity all align, is left to the specific circumstances of specific civilizations at specific moments. We are in one of those moments now. Building the instruments that might detect biosignatures. Listening at radio and optical frequencies for signals. Asking the question. Whether the universe has arranged for the answer to arrive during the window of our civilization's existence, or at all, is not guaranteed. The barriers are real. The universe imposes them on everyone. And the universe offers, as the only alternative, the thin but genuine possibility of light-speed connection, information flowing across the void at the maximum speed physics allows, carrying the full intellectual and cultural content of civilizations that can never share physical space. This is what the universe has arranged, not the meeting, the signal, and the long, slow, silent wait to see if anyone answers. Let us now think about something that the previous layers have been building toward, but never made fully explicit.
The question of what the barriers mean, not just for civilizations trying to meet each other, but for the nature of intelligence itself in a universe structured this way. The universe produces minds. We have established this, at least one instance here. Minds capable of extraordinary things, modeling the cosmos from within, measuring the distance to galaxies,
inferring the existence of structures they cannot see, building instruments that detect the echoes of the Big Bang, asking why they cannot meet their counterparts across the void. These capacities, the cognitive capacities that constitute intelligence at the level of scientific civilization, are immense. They represent the most organized complexity that we know of in the observable universe. More organized in their information processing density than any star, any galaxy, any cosmic structure we have identified. And the universe has placed these capacities in the worst possible location for meeting. Not the worst imaginable location. We established that civilizations near the galactic center face shorter distances, but the worst possible type of location. On a planetary surface, around a single star, isolated from all other stars by the barriers we have described. The most complex, organized structures the universe produces, minds capable of understanding the universe, are embedded in the most isolated structural units of the universe. Planetary systems, individual stellar domains, bubbles of gravitational coherence separated from all other bubbles by light years of near-perfect vacuum. This is the universe's specific arrangement. The complexity is local, the distances are vast, the barriers are real. And this arrangement produces a specific consequence for the long-term trajectory of intelligence in the universe. A consequence that follows from the physics and that is rarely discussed in any context, scientific or otherwise. Intelligence, as the universe has arranged it, is mortal. Not just individual intelligences, individual humans, individual organisms, civilizational intelligence, the accumulated knowledge and understanding of an entire civilizational tradition. Each civilization exists for some finite period, hundreds of years, thousands, millions if they solve the existential challenges we can currently identify. But finite. The sun will eventually die. The planet will eventually become uninhabitable. The physical substrate of any civilization will eventually fail. When a civilization ends, its accumulated knowledge, everything it learned, everything it created, everything it understood, goes with it. Or rather, it goes outward at the speed of light in all directions, dispersing into the electromagnetic background, weakening with the inverse square law, eventually becoming undetectable above the noise floor of the universe. And because civilizations cannot meet, because the barriers prevent the reliable transfer of accumulated knowledge from one civilization to another across the vast interstellar distances, each civilization's knowledge dies with it. The understanding it built of the universe from its specific vantage point, the mathematics it developed, the art it created, the history it experienced, all of it eventually lost. The universe accumulates knowledge locally and loses it globally. It produces understanding in isolated pockets and disperses that understanding faster than it can be reliably transferred to any recipient. It creates minds capable of comprehending vast amounts of reality and then erases those minds without reliable backup. This is not a tragedy in any moral sense. The universe does not intend outcomes, does not value the preservation of knowledge. But it is a description of the universe's specific arrangement with respect to intelligence. And the arrangement is one in which intelligence is fundamentally temporary. Now let us think about whether this is actually the complete picture, whether the barriers are truly so absolute as to guarantee that no knowledge passes between civilizations. Go outside tonight. Find a clear sky. Let your eyes adjust. Give it 20 minutes. Now look up. Pick a star. Any star. The bright ones are easier to find, but the principle applies to all of them, to every point of light visible above you on any clear night. That star has planets, probably. The Kepler mission established that planetary formation is common, that the majority of stars have planets, that planets in habitable zones are not rare. The star you are looking at almost certainly has at least one world orbiting it, at some distance, with some composition, with some chemistry. Whether that chemistry has organized itself into biology is unknown. Whether that biology has produced intelligence is unknown. Whether that intelligence has developed technology is unknown. Whether that technology is currently broadcasting electromagnetic signals is unknown. But the possibility is real for almost every star you can see. And now think about what we have established tonight.
If any of those stars hosts a technological civilization, right now, at this moment, simultaneously with your existence on this planet, you will almost certainly never know. The signal that would tell you is either not being sent, or is being sent but has not reached Earth yet, or has reached Earth but at frequencies or power levels our instruments have not yet detected, or is being sent in some medium we have not thought to look for. And if you somehow learned, if the instruments we are currently building detected a biosignature, a technosignature, a structured signal from that specific star, you would face the full weight of what we discussed tonight. You could not go there, not in your lifetime, not in the lifetime of your civilization, unless your civilization persists for tens of thousands of years and develops energy access we cannot currently conceive.
The star you are looking at, if it has a habitable planet with a civilization on it, might as well be painted on the inside of an enormous dome. Visible, permanent, inaccessible. The light reaches you, the civilization does not. This is not a failure of imagination. This is not a gap in our current technology waiting to be filled by the next generation of rockets or the one after that. This is the physics of the universe, applied to the specific problem of biological organisms trying to cross the distances that physics has placed between stellar systems. The speed of light is 299,792 kilometers per second. The nearest star is 40 trillion kilometers away. The energy required to reach even a modest fraction of the speed of light exceeds the annual energy budget of our entire civilization, many times over, for a single small spacecraft. The rocket equation compounds every increase in speed into an exponentially larger fuel requirement. The biological constraints of organisms evolved for planetary surfaces. The radiation exposure, the bone density loss, the psychological deterioration, the need for food and water and breathable atmosphere across decades of transit, impose limits that shielding and countermeasures can reduce but not eliminate. And behind all of these specific barriers, the most fundamental one, time. The temporal displacement between when information about another civilization was produced and when it arrives at its destination, and the additional displacement between when a physical mission is planned and when it arrives. Any mission to any other star arrives in the future of the world it set out to meet. These barriers do not yield to optimism. They do not shrink with determination. They are written into the laws of physics at the same level of fundamentality as the conservation of energy and the second law of thermodynamics. The universe built these barriers, not maliciously, not by design, as a consequence of the specific values of the physical constants, the speed of light, the masses of particles, the strength of forces that define the universe's structure. The same constants that make stars shine and chemistry work and biology possible also make crossing the distances between stars essentially impossible for any biological civilization. The universe produced intelligence,
possibly in abundance, possibly in trillions of locations across the observable universe over the billions of years of the stelliferous era. Each instance of intelligence embedded in a planetary system, each planetary system isolated from every other by distances that approach impossibility for physical crossing. The universe produced minds and then placed them where they cannot meet. This is the specific and precise cruelty of the arrangement, if cruelty is the right word for the consequence of physics rather than intention. Look at the star again.
Whatever is there, if anything is there, has looked at our star. Maybe. If they have developed the instruments, if they are in the right phase of their civilizational development, if the light from our sun has reached them and they have built telescopes sensitive enough to detect that we are anomalous, that something about the chemistry of our atmosphere is inconsistent with an uninhabited world. If all of that has aligned, something is looking back at our star right now and reaching the same conclusions we are reaching, that the distance is too large, that the energy is too great, that the time is too long, that the barriers are real and compounding and written into the structure of the universe. That meeting is essentially impossible. And perhaps, in the same act of imagination that we are performing right now, looking at a point of light in their sky that is our sun, knowing something is there, unable to go, holding the weight of that specific and permanent impossibility. This is what the universe has arranged, not the meeting, the looking. Two civilizations, possibly, staring at each other's suns from across light years of near-perfect vacuum, in possession of the knowledge that the other exists, or might exist, in possession of the complete impossibility of crossing the void between them. Connected by the light that makes the looking possible, separated by the physics that makes the crossing impossible. Now think about what that means for what you are doing right now, standing under this sky, looking at these stars, thinking these thoughts. You are one end of a possible connection, not a connection that has been made, not a connection that can be made in any physical sense, but the right end of a possible electromagnetic thread, a thread of light that could, in principle, carry information in both directions at the speed of light, arriving years to centuries delayed, carrying the full intellectual and cultural content of one civilization to another. Whether the other end exists, whether any star in your sky has a civilization that could be on the other end of that thread, we do not know. But if it does exist, the thread is already in operation. Our first radio signals are already 120 light years out. The electromagnetic signatures of our civilization, the specific patterns of our technology's output, are already propagating through space in all directions. Any civilization within 120 light years that is listening may already know we are here. We have already sent our first message without meaning to. 120 years of electromagnetic leakage, broadcasting the existence of our civilization to every star within 120 light years in every frequency band our technology uses. The message is already traveling. The barrier to physical meeting is permanent. The barrier to electromagnetic contact is not. And electromagnetic contact, slow, latency-limited, archaeologically strange, temporally displaced, is the universe's provision for connection between civilizations that cannot meet. Not the handshake, the letter. Not the meeting, the signal. Not the journey, the light. This is what the universe offers. Come inside, but carry this with you. Every time you look at the night sky, at the stars that are each a sun, with almost certainly planets, with possibly biology, with possibly minds, you are looking at the full population of civilizations that exist in the universe and that you will never physically meet. All of them. Every one. looking back at you, perhaps, from across distances that physics has made essentially uncrossable. Connected by light, separated by everything else. The universe makes it impossible for civilizations to meet. It does not make it impossible for them to know each other. That distinction between meeting and knowing, between physical contact and electromagnetic contact, between sharing space and sharing light, is the specific and permanent character of what the universe permits. We are the civilization that is, right now, for the first time, developing the instruments to look carefully enough to know. The knowing is within reach. The meeting is not. The universe has arranged both of these facts simultaneously, and tonight, under this sky, you are the instrument at the receiving end of every possible connection the universe allows. Looking at the stars, knowing what the distances mean, unable to cross them, finding out, slowly, whether anyone is looking back. Just let it play.